Hi, we are Team 13, and this is our rule transfer design project. I'm Brittany Sadeh, and I did the lead screw.
I'm Maya Connors and I did the gears.
My name is Shah. I was working on bearings.
My name's Orifa Adilea, and I worked on the bolted joints.
The goal of our project was to design a machine to convey industrial rolls of paper from a manufacturing line to a forklift. The key components that were analyzed were the gears, power screw, bearings, and bolts. The components that were out of the scope were the motor analysis, crank arm, cradle, and the table structure.
Like was mentioned earlier, our key components are our gears, power screw, bearings, and bolts. We also have our cradle arm, which carries the paper rolls, and that is secured to our support table using bearings and bolts, with two gears and mesh to control the rotational movement of the cradle. The motor is located at a length of 0.46 meters from the end of the table, and our power screw is initially inclined at an angle of alpha. The machine operates by starting with the motor. The motor provides a torque which transfers to the torque by which the collar is lowered on the power screw. That torque therefore provides a torque for the larger gear to rotate and be transferred to the smaller gear.
The larger gear transmits torque to the smaller gear, causing the entire system to rotate 90 degrees over a period of 45 seconds.
All right, so we started our analysis with the gears. For this, we assumed a 95% efficiency. Gear 1, which is our driven gear attached to the cradle, we selected a gear with a pitch diameter of 16 inches, 80 teeth, a face width of 2.5 inches, and the material was cast iron. For our driving gear attached to the crank arm, we selected a pitch diameter of 24 inches, 120 teeth, a face width of 2.5 inches, and a material of cast iron. Now, to understand the system, we first started by analyzing how the weight of the cradle and the paper would act on the system. Because we would then need to take that force and apply it to create a torque. And this torque would need to be countered by a torque applied by the gears, since it has to overcome it to move. We also needed to understand the speed and how it would be driven from the bottom gear. So, as we mentioned, the mass of the paper and the cradle play a big role in this design. They ended up having a force of 10.1 kilonewtons, and our torque would then need to be overcoming that. For gear one, or driven gear, we ended up having a tangential force of 19.77 kilonewtons and a radial force of 7.19 kilonewtons to make up that torque of 3.76 kilonewtons that was needed to overcome the torque applied by gravity on the mass. We also had a rotational velocity of 0.33 revolutions per minute, and this was needed to make the 90-degree turn in 45 seconds. Then this would happen counterclockwise. For our driving gear, to supply that force and torque, we need a tangential force of 20.8 kilonewtons, a radial force of 7.57 kilonewtons, a torque of 6.34 kilonewtons, and a rotational speed of 0.21 revolutions per minute in the clockwise direction. Now, for gear failure, we were using cast iron, which we assumed a yield stress of 300 MPa. Our factor of safety needed was 2, and all of our gears were able to have a factor of safety that overcame that.
We were able to optimize the lead screw in our system using the following parameters. As stated before, the crank arm length has to be 450 millimeters. The power screw must complete its movement within 45 seconds, and the screw itself will have one thread with a pitch of 7 millimeters and a mean diameter of 36.5 millimeters. The coefficient of friction we chose from Table 8-5 was 0.11, as we were using steel that is machine oiled for the screw and a bronze nut. Finally, the arm would start off at an angle of 30 degrees. The picture shown shows the start and the end positions of our lead screw. It is to note that it ends and starts at that 30-degree angle. For a lead screw to be considered self-locking, the torque to lower the arm must be greater than 0. The collar torque must also be included when calculating the lowering torque. For our system, we found the lead screw will have a lowering torque of 115.03 Newton meters, meaning that the screw will be self-locking. We also needed to ensure that our lead screw will not fail at the threads. To do this, we calculated the body shear stress due to the torsional moment TR at the outside of the screw body. then calculated the nominal normal stress along with the bearings and thread root bending stress. We then found the von Mises stress along with the maximum shear stress. And because our shear stress is less than our maximum shear stress, we can see that the threads will not fail. To be able to pick the correct power screw for our system, we needed to consider a few more factors. First, we found the minimum length of the lead screw needed would be equal to 1.255 meters. The angular velocity would be 1.67 rads per second. The required torque would be 679.09 newton meters. The required power would be equal to 1.2 kilonewtons. The torque to raise the load would be 117.09 newton meters. And the efficiency of the lead screw would be 35.45%. And the major diameter would need to be equal to 40 millimeters. With these specifications, we were able to find a lead screw on McMaster car that was made of carbon steel with a length of 1.75 meters, along with a matching bronze collar.
When selecting the right bearings for a system, several key factors need to be considered. This include the life expectancy of the bearing, the total external force it will carry, the dynamic and static loads it experiences, and the required factor of safety. In this case, two bearings are being used to support the system. They are expected to operate 16 hours per day, 5 days a week, for 52 weeks a year over a span of 10 years. This results in total required working time of 41,600 hours. The forces acting on the bearings are as follows. The force due to the mass of the paper roll, 8,933.9 newtons. Force due to the mass of the support system, 1,600 newtons. Force from the gears, 14,993 newtons. This gives total force acting on a bearing of 25,497.4 newtons, which is distributed equally between the two bearings, resulting approximately 12,748.7 newtons per bearing. The static load, therefore, is 12.75 kilonewton per bearing. To determine the required dynamic load rating of each bearing, the total number of life revolutions and specific bearing factors must be considered. The total number of the life revolutions required is 832,000 revolutions. The reliability factor, assuming 95% of reliability, is 0.62. The exponent A, which depends on the bearing type, in our case is a ball bearing, so it's 3. These values are used in the bearing life equation to calculate the necessary dynamic load. Resulting dynamic load is 14.1 kilonewtons. With the required factor of safety more or equal to 2, the loads become 25.5 kilonewton for a static load and the 28.2 kilonewton for dynamic load. These values ensure that the selected bearings will meet both performance and reliability requirements under the specified operating conditions. After evaluating available options, we selected a bearing from a McMaster car with the following specifications. Dynamic load rating equal to 52.5 kilonewton, static load rating equal to 35.8 kilonewton, and bore size equal to 55 millimeters. This bearing fully meets our expectations and satisfies all the calculated design and safety requirements.
For our bolt specifications, we chose a 13 millimeter diameter bolt class 8.8 from McMaster car, which is made from medium carbon steel with a proof strength of 580 megapascals. Our tightening torque was set at 159.9 kilonewton meters based on our calculations, and our preload was set to 90% of the proof force, which came to 61.5 kilonewtons. We also designed the system to be held with one bolt per joint of the bearing mount and the support table. In our analysis of the bolts, we considered the total force that the system was providing, which was 25.5 kilonewtons. We also considered the possibility of joint separation between the bearing mount and the support table, and considered the effect of shear loads on the bolts. In our calculations, we took our maximum external load to be 12.75 kilonewtons, which is the total weight from the system split between the two bearings. And the minimum external load was that earlier external load minus the weight of the paper rolls. Using these numbers, our factor of safety against the load, the total load came to 2.99. Our factor of safety against joint separation was 5.88, and our factor of safety against fatigue was 23.19. And lastly, our shear stress was seen to be 3 times lower than the allowable shear of the bolts, meaning that our bolts can withstand the loads of the system and will not fail under any of these conditions. Some additional considerations that we took into consideration were the thickness of the support table, which we set to be 15 millimeters, and the bearing mount thickness, which was 28.6 based on the bearing and bearing mount that we selected.
For our budget, we ended up coming in at $7,604.09. One thing to note about this is that a majority of our budget came from the gears as they were very expensive.
So some of the design strengths were that the starting angle of the power screw allows for the reduction in the tangential force, minimizing the overall force seen in the power screw. And the overall design is compact, as we were able to reduce the size of the arm and power screw. And the bearing factor of safety is well above 2. Some possible failures, it could be failure after lifetime, as we only accounted for the lifetime of the machine. And if maintenance is neglected, the system could fail, as most parts are lubricated.
For future considerations, we see the possibility of using a gear train or using additional gears for our system due to the fact that our current design has really expensive and really large gears. So we see the possibility of using more gears or a gear train to reduce the number and the size and the cost. We also see the possibility of optimizing the timing of the system. We could make this system faster to transfer the rolls in less than 45 seconds.
Thank you.